Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today we are going to study the topic nodes, and there's two types, the radial nodes and the angular nodes. So let us understand what is nodes. It is a region around the nucleus where probability of finding electron is 0. So these nodes are of two types, the radial nodes and the angular nodes. For understanding the radial nodes and angular nodes, I am going to show you some pictures. So now have a very careful observation of the first picture. What is radial nodes? The very first picture represents the radial nodes. So let us understand what is radial nodes. It is a spherical region around nucleus where probability of finding electron is 0. That spherical region is between different S orbitals. Like that spherical region is between the 1s and 2s and 2s and 3s, then 3s and 4s. That is between the two S orbitals. There will be a spherical region where probability of finding electron is 0, and that's called radial nodes. Now carefully imagine the 1s orbital. Here 1s orbital is orange in color. It is just a single s orbital, the 1s orbital, so there will not be any node in case of 1s orbital. Now let's talk about the 2s orbital. The 1s orbital is within the 2s orbital, so there will be a spherical region between the 1s and 2s where probability of finding electron is 0, so that will be called as radial node. So that means if you are talking about the 2s orbital, you will have one radial node. Now let's talk about the 3s orbital. In 3s, let us understand first that 1s is within the 2s orbital and 2s is within the 3s orbital. So there will be the spherical region between the 1s and 2s and a spherical region between the 2s and the 3s where probability of finding electron will be 0. That's called radial nodes. So in case of 3s orbital, you will have two radial nodes, one between the 1s and the 2s and another between the 2s and the 3s. Now let's talk about the angular node. Angular node is the planar region around the nucleus where probability of finding electron is 0. Now that planar region will exist in the p and the d orbitals. Now I have already told you in the lecture of shapes of orbital that p orbitals are having directional preferences and they are dumbbell shape. So there will be a planar region between the two lobes of 2p orbital where probability of finding electron is 0. So in case of 2px, we are having the planar region on the it's like YZ axis. You can have a very careful look on the nodal plane of 2px orbital. Now you can imagine the nodal plane or the angular plane of 2py orbital, and you can easily imagine the nodal plane of 2pz orbital. So these are the pictures of the nodal plane between the two lobes of 2p orbital. And in that nodal plane, the probability of finding electron will be 0. So that's called angular node. So now let's talk about the d orbitals. So this is the picture of d orbitals. In case of d orbitals, I have already told you that d orbitals are double dumbbell shape. So if we are having double dumbbell shape, so that's why you will also have the double nodal plane between the d orbitals. So here you can see the nodal plane. You can imagine the you can imagine the nodal plane in 3 dimensions. In case of 3dxy, 3dxz, then 3dyz, then 3dx square minus y square. But in case of 3dz square, you have to carefully imagine the picture, and you have to imagine the nodal plane in case of 3dz square. So these are the planes, these are the nodal planes where the probability of finding electron is 0. So now let me write some definitions for you. So let's take, I'm writing, first of all, what do we understand by nodes? It is the region around nucleus where probability where probability of finding electron is 0. Now these nodes are of two types. The first one is radial node and the another one is angular node. So what is radial node? It is the spherical region around nucleus between different S orbitals. Where probability of finding electron is 0. Is 0. Now this radial node, I am writing radial node is dependent on principal quantum number, that is small n, and azimuthal quantum number, that is small l. The formula for radial node is, I am writing radial node, or you can write the number of radial node more appropriately. The number of radial nodes is equal to the n minus l minus 1. So now let's come to the angular node. It is a planar region around the nucleus where probability of finding electron is 0. I am writing it is the planar region. Planar region between two lobes of dumbbell shaped orbitals. Where probability of finding electron is 0. Of finding electron is 0. Now the angular node is dependent only on azimuthal quantum number. Angular node is dependent on azimuthal quantum number, that is small l, that is I am writing number of angular nodes will be equal to small l. So now let's evaluate total number of nodes in a specific orbital. So I'm writing total number of nodes. It will be obviously equal to the number of radial nodes plus number of angular nodes. What's the number of radial nodes? We have just evaluated n minus l minus 1. What's the number of angular nodes? It's equal to l. So you will get n minus 1. So that's the total number of nodes. Now let's evaluate radial nodes, angular nodes and total nodes for different orbitals. So here comes the data. So first of all, I have made a table in which I have mentioned the orbitals, the radial nodes with the formula that's n minus l minus 1, angular nodes that's equal to small l, the azimuthal counter number. So total number of nodes will be equal to the small n minus 1. So now firstly let's evaluate this thing for 1s. Now let's evaluate the radial nodes, angular nodes and total nodes for 1s. In case of 1s, the principal quantum number will be 1, and for s the value of l is equal to 0. So let me firstly mention this thing also. I'm writing value of l's to be 0, 1, 2, 3. 0 represents S subshell, 1 represents P subshell, 2 represents D subshell and 3 represents F subshell. So in case of 1s, my n is equal to 1 and l is equal to 0. So the radial nodes will be equal to, what's the value of n? Is 1. What's the value of l? It's 0. And it's minus 1. So it comes out to be 0. So in case of 1s, there is not any radial node. So now let's calculate the angular nodes. Angular node is equal to the azimuthal counter number. In case of 1s, the azimuthal counter number comes out to be 0. So here angular nodes are also absent. So total nodes will be, it's n minus 1 is 1 minus 1, that's also equal to 0. As we are not having radial node or angular node, so obviously its total number of nodes will be 0. Now let's calculate for the 2s orbital. In case of 2s, our principal quantum number n is equal to the 2 and s will be s represents the value of l to be 0. So the radial nodes formula will be equal to the n minus l minus 1. What's the value of n? It's 2. What's the value of l? It's 0 minus 1. So it comes out to be 1. So in case of 2s, we are having one radial node between the 1s and the 2s. Now let's calculate the angular nodes. Angular node is equal to the azimuthal quantum number l. For 2s it comes out to be 0. So the total number of nodes will be 1, that's one radial node, and 0 angular node, so total nodes will be 1. So let's apply it by the formula n minus 1. Here n comes out to be 2, minus 1 comes out to be 1. Now let's calculate for the 2p orbital. In case of 2p, we are having the value of n to be 2 and the value of azimuthal quantum number for p orbital is 1. Now is n minus l minus 1 for radial nodes. So here n is 2, l is 1, minus 1, it comes out to be 0. So in case of 2p orbitals, radial nodes will be absent. There are only angular nodes. Angular node is equal to the azimuthal contour number small l. Here the value of L to be 1. So we get one angular node. So the total number of nodes will be 1. One angular node, radial nodes are absent, so total nodes are 1. So let's apply it by formula. Here n comes out to be 2 is minus 1 rule, so it comes out to be 1. So now let's evaluate for the 3s orbital. In case of 3s, our n comes out to be 3. The value of s to be 0. The value of L to be 0 represents the s. So for 3s, the value of L comes out to be 0. So it's n minus L minus 1. It's 3 minus 0 minus 1. It comes out to be 2. So we are having 2 radial nodes in case of 3s orbitals, because 1s is present in 2s, 2s is present in 3s. So in case of total 3s orbitals, you will get the 2 radial nodes, which I have explained you through the picture that I have shown very first. Now let's evaluate the angular node. Angular node for s orbital comes out to be 0, because the value of L is 0 for the s orbital, so it's 0. So the total radial nodes comes out to be total radial nodes is 2, angular node is 0, so total number of nodes comes out to be 0. It's not 0, it's 2. So the total nodes are 2, the 2 radial nodes and the 0 angular nodes. So total nodes, the formula is n minus 1. Here n is 3, is minus 1, it comes out to be 2. So we got the 2 radial nodes and a 0 angular node, so total number of nodes comes out to be 2. So now let's evaluate for the 3p orbitals. In case of 3p orbitals, our n comes out to be 3. The value of L for p orbitals always comes out to be 1. So here let's calculate the radial nodes. The formula is n minus L minus 1, so it comes out to be 1. So we got the 1 radial node in case of 3p orbital, which I will show you in the diagram which I am going to draw the very next. Now let's talk about the angular nodes. Here angular node is equal to L. Here the value of L to be 1, so we got the 1 angular nodes. So total number of nodes will be 2, the 1 radial and the 1 angular. So the formula is n minus 1 for total number of nodes, so it's 3 minus 1, it comes out to be 2. So we got 2 number of nodes for the 3p orbitals, the one radial and the another one is angular. Now let's talk about the 4s. In case of 4s, the n comes out to be 4 and L comes out to be 0. So the formula is n minus L minus 1. So this n minus L is 0 minus 1, we got to be 3. We got the 3 radial nodes. Now let's talk about the angular nodes. It's 0 because it's s orbital, so no angular nodes will be there. So the total number of nodes are 3 only. The 3 are the radial nodes, so the formula is n minus 1, n is 4 minus 1, so total number of nodes are 3. So now let's talk about the 3d orbitals. In case of 3d, the n is 3 and the value of L for d orbitals or d subshell is 2. So now let's apply the formula for the radial nodes. It's n minus L minus 1, so it comes out to be 0. So in case of 3d, 0 radial nodes are there. Now let's talk about the L. It's 2, so the angular nodes will be 2. So the total number of nodes are 2, that 2 are only angular nodes, 0 radial nodes are there. We got the 2 angular nodes, so the total number of nodes are 3, and by applying the formula is n minus 1, it's 3 minus 1, so we got 2 total number of nodes, which are only angular nodes. No radial nodes are there in case of 3d. So now I have to specifically mention by a diagram the presence of radial node in case of 3 p orbitals. So for that I have made a diagram. I have shown over here that's the x-axis, that's the y-axis, and that's the z-axis. So let's make py is 3py. Let's make it it's a it's a dumbbell shape. So let take nucleus to be present at the origin. My first lobe is in positive y-axis and the second lobe is in negative y-axis. So that's the first of all, that's 2p orbital. I have made 2p. We have to talk about the 3p, right? We have to talk about 3p. Firstly, I have made this orbital to be 2p. So now let's make 3p. The 2p will be present in 3p orbital. So I'm now drawing the 3p orbital. 3p is in shape like this. That's the 3p. So 2p is present within the 3p. That's my 3p. So let me delete the excess. For the timing to make a better understanding, I'm deleting the excess. So hopefully you got the angular plane, and you can easily observe that the angular plane for 2p and 3p is common. So this is the angular plane I'm mentioning. This is the angular plane, or you can say this is the angular node. That's only one, which is common for both 2p and 3p. So now question arises, where is radial node? This is the angular node. Where is the radial node? So let me mark the region where probability of finding electron is 0 between the 2p and the 3p. So I'm marking that region. So the region that I have marked with a pink color, it is the region where probability of finding electron is 0 and which will be called as radial node between the two p orbitals. This is the radial node. Between two p orbitals. Hopefully you got the angular node and the radial node. So that's all for today. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please like, subscribe and share my channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.